So, good afternoon, everyone. Welcome to the week 6 live session on Structural Dynamics course and presented by Danish Vijay from IIT Madras. Okay, so in last week 5, we studied about this forced vibration of single degree of freedom systems, where these systems were excited by impulsive forces, including step pulse, rectangular pulse, and half sign pulse. We derived the a response of the single degree of freedom system to these type of pulse excitations, where the time period of these pulse excitations was much smaller than the natural time period of the system. We derived the time history response of all the three of the single degree of freedom system for all three types of pulses. So in today's class, we will be studying further in this case dampened forced vibrations, where we will be studying about the transmissibility, and also if there was time at the end of the lecture, we will be also studying this effect of damping and base isolation also. So we will then start. Dampened forced vibrations. So in dampened forced vibrations of single degree of freedom system, let us assume that a harmonic force P of t is equal to P naught sine omega t. Sine omega t is being acted upon our single degree of freedom system. With omega, its frequency will be equal to pi by t1. Okay, so as we already know, the governing differential equation for this motion of single degree of freedom system is mx double dot plus cx dot plus k of x is equal to p of t. Okay, this forced vibration response. So in this p of t, we can write it is equal to p naught sine omega t. So we will be having the same single degree of freedom system that we will are studying from last 3-4 weeks. Like this, for example, we are having a block of mass m. It's connected to a spring constant k, and it's also having a dashpot connected to it with code damping coefficient c. Okay, so for this type of system, we can write the governing differential equation of the motion like this, as I wrote here. Here we are having this thing, k here, c here, mx double dot plus cx dot plus kx is equal to 0. So if right hand side has been equal to 0, then we know that it was a free damped vibration, and we know that for free damped vibration, we can write the homogeneous solution for this type of differential equation as x homogeneous solution. We studied it in, I guess, week 4. We can write the solution for this type of free damped vibrations as e to the power minus theta pt, where p is the natural frequency of the system, a cos p dt plus b sine p dt. Okay, sine p dt, or where we define this pd as damped frequency of the system, pd as pd is equal to p times natural frequency of the system times 1 minus theta square, where theta is the damping ratio. Okay, we studied it in the earlier weeks. Now we will be introducing here force also, external force also in the form of P naught sine omega t. So we have to derive the response of a system in presence of this force. So we will be following the same steps we are doing in the earlier weeks like this. We'll divide by m, it becomes mx double dot c by mx dot plus k by m x is equal p naught sine omega t. So here again why I'm doing that thing that we are doing in the earlier weeks, p naught by k and multiplied by k also, and m is again there, k by m sine omega t. Okay, t. Introducing all the substitution that we have x double dot, we can write it as c by m, we write there as twice theta p x dot. Okay, and k by m, we already know k by m is p square, square of the natural frequency, is equal to p naught by k is the maximum static deflection of the system. X naught x static naught. Okay, k by m is again p square is equal to sine omega t. I will write the substitutions here what we made. Actually, we write c by m is equal to twice theta p. Okay, and one more substitution we made, p square is equal to k by m. That's well known. P square equals k by m. We made this substitution here. Okay, so let's now assume we have to find a particular solution for this differential equation. Okay, so for the same thing we will assume, let's assume that its particular solution has the form x of t. Now it's particular. Okay, let's assume it has the form m sine omega t and m sine omega t plus n cos omega t. We are only making this assumption. Okay, so now we require here x double dot, we require x double dot and x dot, and x we already assumed for making substitution in this equation, number, okay, equation number 1 for making substitution in equation number 1. Okay, so we will differentiate this equation once. X of t pi will be equal to m omega cos omega t. Okay, and this will be equal to minus n omega sine omega t. Okay, and once again differentiating the above equation, we will get x double t pi is equal to minus m omega square sine omega t, and this will be again minus n omega square cos omega t. Okay, cos omega t. So we have to do one thing, we have to let's, this will be, this equation will be whole, we call this as equation number 2. Okay, so when we substitute equation 2 in equation 1, okay, we will get this type of thing. We will get minus m omega square sine omega t. We will have minus n omega square cos omega t, because we are having x double dot, and then we have twice theta p times x dot, and x dot, our x dot is m omega cos omega t minus n omega sine omega t. Okay, then we have the last thing is p square times x, p square, and our x already assumed is m sine omega t plus n cos omega t. Okay, so far we are just making assuming the form, taking the differentiation twice and substituting back into the governing differential equation. Just simple steps we have to follow. X static naught, it's equal to x static naught p square sine omega t. Okay, so if we will collect here the terms of sine omega t, all sine omega t terms we will collect here, and we will collect all cos omega t terms here. Cos omega t term is here, cos omega t term is here, and we are having cos omega t term here. Okay, so we will be collecting all the like terms like this one. I will write here minus m omega square 1, and then is twice theta p and omega, one more term, and I am having one more term p square m. Okay, p square m, and it's associated with sine omega t. Okay, then one more thing, we will collect terms of cos omega t. Okay, cos omega t is having minus n omega square, okay, plus twice theta pm, twice theta pm times omega plus n square p. Okay, and np square, sorry, np square cos omega t, and this whole is equal to x static not sine p square sine omega t, p square sine omega t. So if I compare the left hand side with right hand side, I will get these two equations. So you are seeing here the coefficient on the left hand side, we are having sine omega t and cos omega t terms here, and we are having on right hand side only sine omega t. So comparing the coefficients on the left hand side with the right hand side, we will get minus m omega square minus twice theta p n omega plus p square m. So sine omega t is same, so their coefficients will be also equal, and it will be equal to x static naught plus p square. Okay, this will be 1 2, this will be third one. Okay, then comparing the coefficient of cos omega t, and on the right hand side cos omega t has coefficient 0, so it will be minus n omega square, so it will be minus n omega square plus twice theta p m omega plus n p square is equal to 0. Okay, is equal to 0. So I will be making one more thing here. I will be writing it like this, m and collecting terms of m and n also, so it will be easy for us. So we will be writing here. So for example, so for this case, we will be writing here m times p square minus omega square minus twice theta p omega n, okay, is equal to same thing, x static not p square. This just this one rearrange it little bit, and here again we will be doing same rearrangement, collection of the like terms. We will be having so here we will be having n p square minus omega square, p square minus omega square, and one more thing, we will be having twice theta p omega n, twice p omega m, here it will be equal to 0. Okay, so we are seeing that we are having two simultaneous equations in m and we are having only two variables. So when we solve these two equations 3 and 4 simultaneously, three and fourth equation, so solving 3 and 4 simultaneously, we will get m is equal to, m will be equal to 1 minus omega p ka whole square. We'll be getting long expressions. Okay, one more thing we will be getting is like this one, 1 minus omega by p over whole square plus 4 theta square omega by p ka whole square, and we will be getting n as twice minus one more thing will be there, x static naught. Okay, important, minus twice omega by p times theta, and it will be again denominator will be same. Okay, here like this it will be sin of again x static of 0. Okay, so if we make a substitution here, omega p is equal to 0, omega by p will be equal to not 0, sorry, 5, and we call this as frequency ratio. Frequency ratio, because you will be seeing that it is the ratio of the frequency of the external excitation omega to the natural frequency of the system p. Okay, so we will get these terms little bit simplified, not that much, but to some extent. M will be equal to 1 minus phi square divided by under root of, sorry, not under root right now, 1 minus phi square over whole square plus 4 theta square phi square. Okay, 1, and this will be x static naught. One more thing, n will be equal to minus twice theta phi divided by 1 minus same denominator phi square whole square plus 4 theta square phi square x static naught. Okay, we got our two coefficients for this, like this one. Okay, so our particular solution will be of form like this one. Substituting m and n in this one, second equation. Substituting value of m comma n in second equation. Okay, second equation we will be getting x of t particular is equal to we will be getting this one, m times it will be actually like this. We have m sine omega t plus n cos omega t. Okay, omega t. Okay, so both in both m and n, x static naught is constant. Okay, we have x static naught constant, so it will be common for both the things, and we will be having 1 minus phi square m, and this denominator is also constant, so we'll be taking it outside. Okay, 1 minus phi square over whole square plus 4 theta square phi square. Okay, and then we have this thing. We have sine omega t. First we have 1 minus phi square coefficient of m, numerator of m, sorry, 1 minus phi square sine omega t. Okay, and we have then coefficient minus twice theta phi coefficient cos omega t. Okay, it is, and this cos omega t. Okay, okay, this one. So if we make the substitution here, like this one, if we put sine alpha is equal to twice theta phi divided by under root of 1 minus phi square over whole square plus 4 theta square phi square. One substitution, and another substitution we will make sine. We will have cos alpha is equal to 1 minus phi square divided by same denominator. 1 minus phi square over whole square plus 4 theta square phi square. Okay. So we are doing this smart trick only so as to bring this whole thing here in terms of this sine a minus b. Okay. So because we know sine a minus b is equal to sine a cos b minus cos a sine b. So we are having sine a and we are having cos a here. So we are assuming this to be 1 minus phi square divided by root under 1 minus phi square whole square 4 theta square phi square as another thing. Cos b here is cos alpha and sine alpha is here 2 theta phi 1 minus phi square whole square plus 4 theta square phi square. Okay. So when we will substitute it in this one. So for example, we are having this. So to get 2I theta phi is there, like 2I theta phi is there, 1 minus phi square is there. Those are in the numerators. But we are dividing it by 1 minus phi square whole square, this one denominator. So we will have to multiply but with the same. So we will be having x of t particular integral. We are having x static naught. So we are multiplying by this thing 1 minus phi square whole square plus 4 theta square phi square, one thing, and denominator we already have 1 minus phi square whole square plus 4 theta square phi square. Okay, then we substituted this thing. So 1 minus phi square is there. First is 1 minus phi square we are having. So we multiplied by this, we will divide with the same also. 1 minus phi square whole square plus 4 theta square phi square, everything is in square root, sine omega t. Okay, sine omega t, and we are having minus here twice theta phi. Okay, twice theta phi divided by, and we are having the same denominator here, root under 1 minus phi square whole square plus twice theta phi, or we can write twice theta phi ka whole square actually is 4 theta square phi square. Okay, cos omega t. Okay, omega t. Okay, and so when we make substitution of these two things, sine alpha and cos alpha, this whole equation will boil down to, so you are seeing here is square root, here is not square root, so there will be one square root will be left in the denominator. Okay, simple mathematics. X static naught divided by, you people are supposed to do this steps by yourself. Okay, and this one this will be x static naught, this will be 1 minus phi square or whole square plus 4 theta square phi square. Okay, so this whole equation will boil down to sine omega t, and 1 minus phi square divided by whole is equal to cos alpha. Okay, sine omega t cos alpha, and similarly it will be equal to cos omega t sine alpha. Okay, can back check it also. Okay, so this is actually equal to, this whole is equal to x static naught under root of 1 minus phi square whole square plus 4 theta square phi square. This will be equal to sine omega t minus alpha. Okay, sine omega t minus alpha. X of t particular solution. Okay, for our forced vibration problem. This is a particular solution. So we can write the total solution for our problem like this one. Total solution will be equal to total solution total solution will be x of t is equal to x homogeneous plus x particular. Okay, both will be the function of time. So we will be having x of t will be equal to e to the power minus theta p t a cos p dt plus b sine p dt. Okay, and we have to add particular solution as this one. I will write it by different one. Okay, I will write it as x static naught sine omega t minus alpha divided by 1 minus phi square over whole square plus 4 theta square phi square. So this is the total solution for our problem. Okay. So you are seeing here two types of responses here. One we call as this we call as transient response. This one transient, and we call this as steady state response. Steady state response. What is the difference between the transient response and the steady state response is that the transient response decays with time. So, but the steady state response will be there till the force or the external external excitation is being acted on our single degree of freedom system. This transient response will die because of the damping present in the system, and this steady state response will continue to be there in the system. And one more important factor here we are having in the substitution, that sine alpha by cos alpha, if we divide sine by cos, we will get getting tan alpha. We're getting one more important parameter, tan alpha here as. You just keep note of that. Tan alpha will be equal to twice theta phi upon 1 minus phi square. 1 minus phi square is more important. Later on we will require this. Okay. So if we will see now the transient response of our system after a long period of time, for the steady state response of our system after a long period of the time, then when the transient response has fully decayed because of the damping of the system. So then we are interested in the steady state response of the system only. So if we take this steady state response only, this one, x of t, so I will be denoting it with the same x of t only. So as to avoid the confusion, x of t will be so it is equal to x static naught sine omega t minus alpha, sine omega t minus alpha, and I am having the denominator as under root of 1 minus phi square over whole square plus 4 theta phi square whole square. Okay, 4 theta square phi square. So I call this as steady state response. Steady state. Okay, and I'm only interested in this steady state of response. So if I see that how the response, that's the dynamic response. You people are aware with this. This is the dynamic thing because it's changing with time. Dynamic response. If I see the ratio of the dynamic response and the maximum static response of the system, okay, I will be getting a ratio like this: sine omega t minus phi, omega t minus not phi, alpha divided by under root of 1 minus phi square over whole square plus 4 theta square phi square. We call this as amplification, dynamic amplification factor. Okay, dynamic amplification factor. Okay, so what this dynamic amplification factor does, it is actually tells us how much the dynamic response is amplified with respect to the static response of our system. So whether it is greater than the static maximum static response of our system or it is less than that one. So it's all governed by this dynamic amplification factor, this one. So this factor depends upon a number of parameters. If you can see from the equation itself, it depends upon depends upon number of parameters. So if we see number of parameters, first and the important one is omega. That's the frequency of external excitation. External excitation or force, whatever. Okay. And one more important factor, it depends upon the P, natural frequency of system. Frequency of single degree of freedom system. Okay, it depends upon one more important parameter, phi. That's the frequency ratio omega by p. And more importantly, last but not the least, that is the damping of the system or the damping ratio. Theta is equal to damping of system. Okay, these four factors, this dynamic amplification factor depends. Okay, so we can see here, for example, if we want to plot this dynamic amplification factor RD with respect to the frequency ratio, that's 5. So we have to do things like this one. So for example, I plot phi on x-axis like this one. Okay, I plot this phi here. Okay, it's omega pi p. Ratio of the frequency of the external excitation to the natural frequency of the system is known as dynamic this frequency ratio. Okay, on y-axis, if I plot this RD like this one, so I will mark one important value here, that's dynamic amplification factor is RD is equal to 1. So that is the dynamic response of the system is exactly equal to the maximum static response. And then the RD is equal to 1. So in the equation, from this equation, you see if it's equal to 1, so x of t is equal to x static naught. Okay. And one more important point here is, important value here is omega pi p is also equal to 1. That is when omega external excitation frequency is equal to natural frequency of the system, omega is equal to p. Okay, this is equal to implies phi is equal to 1. Okay, and one more important thing that I already told you, x of t is equal to x static naught. So when this condition will occur, we will be having RD is equal to 1. Okay, so if we people can see from this equation, for example, if we induce phi is equal to 1 in this equation, okay, so this equation, sine omega t minus alpha divided by root 1 minus phi square 4 theta square phi square. Okay, so if phi square is equal to 1, our RD will be equal to, so I will write here, then we will plot. Okay, so at the rate frequency ratio omega, that is phi is equal to omega by p is equal to 1, we will get our amplification factor is equal to 1 by twice theta. Okay, twice theta. So amplification factor will be inversely proportional to the damping of the system. One of the important things that we noticed. Okay, and when this amplification at the rate frequency ratio is equal to 0. So if we put here everywhere 0 here, 0 here, we will get this x of t is equal to this amplification factor like this one. So first we will draw this one, two lines here, one line like this one, and one more line along the mark that, okay, this one. So okay, we are having like this one. So we saw that the graphs will be like this. For example, if we take certain damping ratio, and our RD will be like this one. Initially, if the damping this one frequency ratio is less than 1, frequency ratio is less than 1, our RD will be increasing with this one, like this. This one, and then it will be again decreasing here. Okay, it will start decreasing like this. Sorry, it will again start decreasing like this. Okay, this will be the curve, this one. So we saw that it is inversely proportional to the damping. So for example, if it is for a damping ratio of 0.01, for example, not 0.01, it is for a value of theta is equal to 0.1. Okay, so if we choose some higher damping like 0.2, so that response at maximum response, that's phi is equal to 1, it will further reduce. It will again start from this one. Okay, up to this point it will come here, it will reduce, maximum response will go, and it will again tend to go like this way. And for other this value is for theta is equal to 0.2, higher values. And if we choose further higher values, excessive damping, because I already told you in structural systems we take up to 0.5 this damping. So if we take some higher values, for example, we choose 0.7, and that's excessive damping. So this will be having a response like this. It will be always decreasing with the frequency ratio response like this. it will be like this. It will be for theta is equal to 0.7, 0.7 theta. And it's if it is highly damped system, that's theta is equal to 1. It will be like this one. Okay, theta is equal to 1. So if the damping is very low, mm, so we will be having like this one. This is for theta is equal to very low damping 0.01. So you people can see that how much important role a damping plays in our in the response of our single degree of freedom system. So for example, if the damping was not present in our system, the response will shoot up to infinity at a frequency ratio is equal to 1. But it's only the damping in our system that converges the response there to some finite values. Otherwise, you can see that this damping, this amplification, dynamic amplification factor will shoot up to infinity here. So at phi is equal to 1. Okay. So this is the thing. From here, we can clearly see that amplification factor at a constant frequency ratio is of 1 is equal to inversely proportional to the damping. Now we can have transmissibility. Important topic. One more important topic is transmissibility of our system. Transmissibility. Transmissibility. Okay. So for example, we are having our single degree of freedom system like this. We're having a single degree of freedom system like this. Okay. Log of mass m, and it's having its dynamic characteristics. The already stiffness of the system is k. So it's just a mathematical model. I already told in the first classes that it's just a mathematical model of single degree of freedom system, mathematical representation. Okay, so I'm just always showing you this spring type stiffness in our single degree of freedom system. So for example, if we take a frame structure or a building structure, there is the stiffness is contributed by n number of factors. For example, stiffness is contributed by the bending stiffness of the columns. Stiffness is contributed by the actual stiffness of the columns. It is the stiffness contributed by the beams. All the members that are there in our system, stiffness is contributed by everyone. So for this our convenience and the mathematical modeling of our single degree of freedom system, we show it like this one. And this dashboard also is just a mathematical representation how the damping looks like. Actually, we are having, if we are using only viscous damping only, but in our actual structural systems, the damping is only because of the friction, the drag, the friction between the joints, and all the other factors. So if it's K and C, like this one, it's supported on a system like this. Okay, so for example, this mass M is being excited by some external excitation, P of T, okay? And this P of T is again, we already solved for it, P naught sine omega T, so it will be easy for us. Sine omega T. So for example, it is being excited by this excitation, P is equal to P naught sine omega T, okay? So we are interested in finding how much the force is being transmitted to this base. Okay, so for example, this is some machine, some big machine in our somewhere in the workshop. This big machine is there. It's on the some first floor, second floor. So we have to design the floor system. We have to design the slab for this one. So we have to require this information regarding how much force so this machine is operating with some frequency, circular frequency omega. So we have to know that how much of this vibrations will be transmitted to our floor system in order to design it. So for example, if that vibrations induced by this machine to our floor system will be excessive and exceed the limits of our slab, so eventually there will be failure. It will be very catastrophic for our building and all the other structures. For example, in our bridges, there is a vibration induced by huge vehicles, very huge vehicles, trucks and all. So we have to do the vehicle bridge interaction first, how much vibration will be induced in our bridge deck, and then we have to design those decks according to those systems. So in order to arrive at the final solutions, we require the knowledge of this transmissibility ratio. So for the same, we are deriving it here. Okay. So x of t, for example, it's having, since it's single degree of freedom system, so it's having motion like this, like x of t is just like this. Okay. So we already know its steady state response x of t will be given as, just few minutes ago we derived it as maximum static deflection over a system, x static naught sine omega t minus phase angle alpha divided by under root of 1 minus p square whole square plus 4 theta square phi square. Okay. And so we are interested in finding the force that is being induced in this system. Also, for example, if force f of t is being induced in our system, f of t, okay. So we know that this f of t will be just induced. This f of t is just the reaction of the forces that is being there due to the stiffness of the system and the damping of the system. So f of t, our f of t that is being induced in our system will be just the summation of the restoring force that our system offers, k of x, and the damping force that the damping in the system offers, cx dot. Okay. This is actually the force transmitted to our base. Okay, force transmitted kx plus cx dot. Okay, and we can see that kx plus cx dot is actually is equal to p of t minus the inertial force mx double dot. Okay, very easy so far. So we can put we are having x of t here. We will just differentiate it once to get x dot of t. Okay, just easy things here. So for easy, x dot will be equal to x static naught sine omega times cos omega t. Okay, omega t minus alpha whole divided. Sorry, I just created a mess there. I will write it somewhere else. So I will find x dot of t as x static naught omega cos omega t minus alpha under root of 1 minus phi square 4 whole square plus 4 theta square phi square. Okay, this is the thing. So when I substitute these things in equation first, so what was the equation number lastly we used something 4, so equation 5. So substituting x comma x dot in 5, we have, okay, we will be having just I'm doing it fast. We will be having f of t transmitted to our system as x static naught. Then this will be denominator. I will take common. Okay. One smart thing I am doing here, I am doing denominator d is equal to, because I have to write it everywhere. D is equal to 1 minus phi square whole square plus 4 theta square phi square. I'm doing this one thing. Okay, so I will write a denominator here. So I have k sine omega t, sine omega t minus alpha, one thing, and another thing I have c omega, c times omega cos omega t. Okay, minus alpha. Okay, this one thing. Okay, so uh, uh, I'm taking this k as common. It will be x static naught divided by k divided by, sorry, uh, yes, we are dividing by k throughout. Not, we will not be dividing by k. We are actually writing this because we know na our x static naught is actually nothing. P naught divided by k. Okay, that is the maximum amplitude of excitation force divided by k. So we will be writing it as P naught divided by d. So k will go inside and it will cancel k. It will be sine omega t minus alpha. Okay, so it will be plus c omega by k cos omega t minus alpha. One thing. Okay, this is there. So it's p naught by t. So we can write omega c by k as here I will make substitutions very fast as c omega by k is equal to c omega by k is equal to for c we will be writing twice theta root km is the formula for c, and omega is there divided by k. Okay, when we will solve it further, it will be equal to twice theta omega by p. Okay, and omega by p we know it's the frequency ratio twice theta p. So we will substitute it back. Our equation will boil down to p naught by d sine omega t minus 5 t minus sorry, not 5 alpha plus twice theta phi cos omega t minus alpha. Okay, I will do one smart thing here as p naught I will multiply by under root again so as to make in the form of sine a plus b. Okay, I will do 1 plus 4 theta square phi square. Okay, divided by denominator is there already. Okay, d, and my equation will look like this. It will be 1 divided by under root of 1 plus 4 theta square phi square sine omega t minus alpha, sine omega t minus alpha plus twice theta phi cos omega t minus alpha divided by denominator again here. Okay, root under 1 plus 4 theta square phi square. Okay, closing the brackets here, and I will make the substitution like this one. I will take this as cos alpha is equal to 1 by root under 1 plus 4 theta square phi square, and sine alpha is equal to twice theta phi divided by root under 1 plus 4 theta square phi square. Okay. So this one. So when I substitute it here, it will be like this. P naught by D, my f of t will be equal to P naught by D under root of 1 plus 4 theta square phi square sine omega t minus alpha cos gamma. Okay, we are now giving the substitutions, and another one is cos omega t minus alpha sine gamma. Okay, sorry, I wrote here alpha alpha, it's gamma. Okay, it's new substitution, cos gamma sine gamma. Cos gamma is this, sine gamma is this. Okay, so our equation will boil down to P naught by D under root 1 plus 4 theta square phi square sine omega t plus gamma minus alpha. Okay, f of t. Okay, so I told you we have to see the ratio of f of t to p naught. Okay, f of t divided by p naught will be then equal to, and I am writing the value of d also as this one, as 1 minus phi square over whole square plus 4 theta square phi square, and this is under root of 1 plus 4 theta square phi square sine omega t minus alpha sine omega t, in fact plus gamma minus alpha. Okay, this is our transmissibility ratio. Okay, ratio. Okay, so again few people will be seeing here, it depends upon a number of factors, damping ratio, frequency ratio phi, phase angle gamma alpha, and more importantly, this frequency ratio is importantly dependent upon the frequency of the external excitation and the frequency of natural frequency of the system. Okay, so it's maximum ratio, so we will write our transmissibility T as, now like this one, T will be equal to under root of 1 plus 4 theta square phi square under root of divided by root under 1 minus phi square over whole square plus 4 theta square phi square. Okay, so at the rate when frequency ratio phi is equal to 0, our transmissibility ratio TR is equal to 1. If you induce phi is equal to 0, TR will be equal to 1. At the rate phi equals 1, transmissibility ratio is equal to root under 1 plus 4 theta square phi equals 1 divided by 2 theta square. Okay, now 2 theta. Okay, so you people are again seeing here the transmissibility ratio is being controlled by the damping of the system. If we have a highly damped system, so our transmissibility ratio will be low, and if we have very light damped system, transmissibility ratio will be very high. So transmissibility ratio, we have to design our structural systems on the desired range of the transmissibility, how much transmissibility we require, it depends upon that. So the damping ratio, damping to the system, we can provide accordingly. Okay. One more important value is there. If frequency ratio phi is equal to under root 2, it's an important ratio there. So at that point, transmissibility ratio is equal to 1 if phi is equal to under root 2. Okay. So if we want, for example, there are some structural systems in which we are giving vibration to one system, and we want this whole vibration to be transported to the base or something else. There is another structural system connected to it. So between these two structural systems, we want the transmission of the vibration to be 100%. So in that case, we have to ensure that the natural frequency of the system to which the vibration is to be transferred should be matching with the it should be at least external, that's omega, external frequency of the vibration of the force should be root 2 times the natural frequency of the system to which we want transmissibility equal to 1. And another one is at the rate of phi. If our phi is infinity, our transmissibility ratio will drop down to 0. Okay, I will be showing you these things. And one more important thing is at phi is equal to 1, transmissibility ratio is inversely proportional to damping. Same like in case of dynamic amplification factor. Okay. So for example, we are having frequency ratio x is like this one. We're having frequency ratio x is like this one. Phi is equal to omega by p, and we are having two important values on it. Omega is equal to 1, phi is equal to 1, and phi is equal to under root 2. That's something like here, under root 2. Okay, we're having one more axis for this one. What is this for transmissibility ratio TR? Okay, transmissibility ratio TR. Ratio. Okay, transmissibility ratio is on this axis. Okay, so we are having transmissibility ratio. We're having transmissibility ratio here 1 again. For example, it's 1 here also. So same like this one. This we're having one more thing here. One axis, and one important governing value is their root 2. Okay. Okay, we're lying this one. So if the damping is very light, our transmissibility ratio initially increases. Our transmissibility ratio initially increases like this one, and at it is called under root 2. Sorry, it initially increases, and at under root 2 it will pass through 0. Not pass through 0, or it will pass through 1, and then again it will be like this. Okay, for example, we are choose our damping very light, theta is equal 0.01. We choose some higher dampings, like we are taking 0.1 damping. It will be like this same, but it will go through like this, this. And for other damping, higher damping values, the graphs will be like this. First going like this, then passing this point like this. Okay, and then other graphs like another one. Okay. So like these things, for example, I will write this is theta is equal to 0.1, theta is equal to 0.2, theta equals 0.7. Okay. So this is the transmissibility graph. This is a very important graph in the dynamics. So that's all for today. Thank you everyone for joining today's session. See you next week.